In this video, I'm going to look at rigid bodies resting in limiting equilibrium. In practice, this means that the friction force will be at its maximum, F equals mu r. Now let's look at one example. Here we have a ladder leaning up against a wall. A uniform ladder, length 6 meters, and mass 30 kilograms. Easy. Bottom end of the ladder is on rough horizontal ground, and the top end rests against a smooth vertical wall. The angle is 70 degrees with the horizontal. A man of mass 80 kilograms stands on the ladder, 4 meters from the bottom. If the ladder is in limiting equilibrium, find the coefficient of friction between the ground and the ladder. Well, I would like you to have a go at this for yourselves. So pause the video, piece of paper, decent diagram, all forces, and work through it. You should be able to cope with this with the mechanics that you know. So just pause the video. Well, have you managed that? I will do it all in detail right from the beginning for those of you that had a problem. So the first thing we need to do is to look at some forces. We want to put forces on the diagram. Well, it's on rough horizontal ground, so there will be a force, F, we'll call it, of friction on the ground, and that must be acting towards the wall to stop the ladder slipping away. There will also be a normal reaction from the ground acting on the ladder, and we'll call that one R. In fact, we'll call it R1 because we are going to have another reaction. Right, now let's look at the top end of the ladder. At the top end of the ladder, it's against a smooth vertical wall. Therefore, there's no friction, no force moving up and down, just a normal reaction acting outwards. Well, it would be if it drew in the right place. Let's just make that one look, I hope, a little bit better. And there is the normal reaction, let's call it R2, at the top of the ladder. Okay, one or two more forces to put in. We've got the weight of the ladder. Well, the ladder is uniform, so the weight will act exactly in the middle and vertically downwards. Let's make that look a little bit more vertical. He said, hopefully. And the mass of the ladder is 30, so the weight is 30g. We have a man of mass 80 kilograms on the ladder. So we need to put a man on the ladder, and he's 4 meters up from the bottom. So we have a man on the ladder. Weight, 80 kilograms, just getting the colors right, I hope. And therefore we have a force down acting on the ladder, everything's in equilibrium, that must be equal to the man's weight, which is 80g. Any more forces to put on the ladder? I don't think there are. We just need to make a note of one or two things, that this distance is 3, this distance is 1, the whole distance, of course, is 6, so we've got all of that. Let's put the angle in. The angle there is 70 degrees. If that angle is 70, then these two angles will be 20 and 20, and the angle at the top will also be 70. Right, I think now we've got enough on that diagram to be able to solve the problem. Right, I've moved the diagram down a bit so that I've got room to write and we can still see the diagram. Well, the first thing I'm going to do is to take moments about the bottom of the ladder. Let's call it A. So if we do moments about A, then if we take the weight of the ladder, that's 30g, resolve it, you get 30g sine 20 times 3. 30g sine 20 times 3. You'll also get the moment due to the weight of the man acting on the ladder. So you have 80g sine 20 times 4. 80g sine 20 times 4. Those are both clockwise. The reaction at the top will give us an anti-clockwise moment. That will be R2 sine 70 times 6. And the whole purpose of taking moments about the bottom was that the moment of F is 0, the moment of R1 is 0. So we now have the moments of all the forces about A. The equation has only got one unknown in it. So after pressing one or two buttons, we can discover that R2 is equal to 243.7387 and lots more numbers. I want to keep all the numbers because I need to use R2 later. Well, if we want the coefficient of friction and we're in limiting equilibrium, F equals mu R1. I need to know F, I need to know R1. I've taken moments. Usually when you've taken moments once, the best thing to do next is to resolve in two different directions. Let's resolve, first of all, horizontally. If we resolve horizontally, at the bottom of the ladder we have F. At the top of the ladder we have R2, and there are no other horizontal forces. So we now know that the frictional force is the same as R2, which is 243.7387, etc. Well, what happens if we resolve vertically? Forces have got to balance out. There's R1 acting upwards, 30g acting downwards, 80g acting downwards, nothing else. So we get R1 is equal to 30g plus 80g, which is 110g. Limiting equilibrium. Means that the friction must be at its maximum. And that is mu R1. And therefore mu, let's make that look a little nicer. Mu is equal to F divided by R1. F is 243.7387, etc., divided by 110g. That gives us that mu is equal to 0.23 to two significant figures. Right, so that's what happens with a ladder. I want to look, before we go away from here, what do you think would happen if instead of putting the ladder at 70 degrees, I put it at, say, 50 degrees? Do you think the coefficient of friction would be the same? Or more? Or less? If I was to put the coefficient of the ladder at an angle of 50 degrees, what would happen to the coefficient of friction? Well, as you put the ladder further out, so I hope you can see it's going to be easier to slip. If it's easier to slip, we're going to need a bigger coefficient of friction. I have actually worked it out. If you had 50 degrees, you would need a coefficient of friction of 0.74, over 3 times as big. Perhaps it's easier to see it in reverse. If the ladder is nearly vertical, then there isn't much reason to slip. We wouldn't need such a big coefficient of friction. Now, if you take 80 degrees for your ladder, you would need 0.11 as your coefficient of friction. So if you are going to go climbing ladders, my advice is to put the ladder fairly close to the wall to have a steep angle. Then you need a smaller coefficient of friction. If you put the angle like that, you will need a much larger coefficient of friction. You're much more likely that the bottom of the ladder is going to slide away and you are going to come downwards. Not a good idea. That did happen to me when I was about 15 or 16, painting the outside of my parents' house. I put the ladder at too shallow an angle and it just slipped while I was on it. So that's one precaution you should take if you are going to climb a ladder, a steep angle. Now let's suppose that two of you have taken a ladder out and you're putting it up against a wall. You want to go up to the top of the ladder to mend a window or to do something at the top. Firstly, you're going to choose a steep angle after what I've just said. There are two of you. One of you is going to climb the ladder. Whilst that person is climbing the ladder, can you think of anything useful that the other person could be doing? Or should they just make a cup of tea? What could the other person do to help, to make it less likely that the ladder will slip? Well, quite simply, the other person can just stand on the bottom rung of the ladder. If the person stands on the bottom rung of the ladder, they will, by standing there, increase the reaction at the bottom. If they increase the reaction at the bottom, they will increase the maximum friction force. They will make it much less likely that the ladder slips. This is actually a regulation now in England that if you have somebody going up a ladder, I think more than a certain height, there must be a second person standing on the ladder. They don't have to hold the ladder in or anything like that. Stand on the bottom rung of the ladder, increase the reaction, increase the maximum friction force. So there is some practical use in your mechanics lessons. You'll be glad to hear that, I'm sure. You can find more about this if you look in your textbook, M2, on pages 141, just turning it over to 146.